Everyone, I'm Pietro de Marchi. I'm glad to be part of this competition. Today we'll talk about the estimation of the potential impact of solar power satellites on space environment stability via stochastic network analysis. Here are also named my team members, Niranjana and Josh, and the faculty advisors, Massimiliano, Vasile, and Yirui. We are from the Department of Mechanical and Aerospace Engineering of the Aerospace Center of Excellence, University of Glasgow, and this project is also partially co-founded by ESA. So we already know what is a solar power satellites, and here we can see two main examples. So the LEO reflector, the concept developed by ESA on the left, and the GEO Cassiopeia model concept developed by Space Solar, a UK company. These two prototypes have the main characteristic of solar power satellites, so the very huge and peculiar dimensions. One harvesting sun energy by reflection, and the other one by concentration and then transmission back to Earth with the helix. So main studies so far have focused on assembly, re-entry, power collection, and mission analysis for solar power satellites, while there's a huge gap on this study, which is mainly focused on which is mainly missing, and which is about the estimation of consequences of a collision with a solar power satellite on the rest of the space population already in orbit. So both active and inactive objects up there. So the main goals of the present study is to develop a framework to have an actual simulation of the space environment that allows us to better quantify the risk for a space solar power satellites mission. Develop also a custom breakup model to better account for the impacts with solar power satellites, so a custom tailored breakup model for these huge structures, and a definition of some metrics to assess the environmental impact of these missions. So what have we done so far to face these goals? So here the framework that we have developed. So once we know the population, the background population in LEO or GEO, considering also the solar power satellites missions, these data are inputted inside our evolutionary model, which is NESI, the network-based evolutionary model, where inside there are different modules. The modules we are interested in are the livelihood computation, so the first module that better allows us to estimate the probability of collisions of any object with the solar power satellites, a breakup model, which allows us to better estimate and quantify the consequences of impacts of any objects with the solar power satellites. And once we compute the evolution of the space environment in time, we have after some metrics that allows us to understand the impacts of collisions with solar power satellites along time for different orbital shells and different missions. So here we analyze all the main blocks we have seen before in more detail, just to give a better understanding of how the models actually work. So the first one is the collision likelihood module. So this module we develop some probability density function to better estimate the risk of each subcomponent of the solar power satellites structures um, to collide again against any other objects in the space um, environment. So again, this probability density function can better account for this for the peculiar shape of the solar power satellites um, characteristics. The breakup model part instead is a custom breakup model that combines the classical approach, like for example, as it is employed in the NASA standard breakup model, and an innovative method that consider a series of primitives subcomponents of each structure. And once an object collides with these primitive sets, we compute which primitives or which subcomponent is actually separating or breaking up. Here we can see on the image on the right a very simple example against with a truss structure which is impacted by a fragment, the blue point, and as plotted in the figure, we see that the violet trusses are those breaking up, while the red dots represents the breaking up joints of the truss structure. So with this model, we can actually better estimate the fragmentation for any type of structure, of the typical structures of SPS. And again, the last part is the health metrics. So we develop a series of analytics that allows us to better account for the risk, so to better estimate the risk for the other missions at different orbital shells once a collision happened with this solar power satellites mission. All this information, all the previous modules come together inside the NESS evolutionary model, which is the network model developed at the Aerospace Center of Excellence to estimate the evolution of the space environment in LEO and GEO environments, considering four types of object species, so the payloads, upper stages, non-maneuverable, and fragments that can interact through the altitude and inclination beams inside the network model via collision interaction or decay interaction. At the moment, we can consider fragments bigger than 10 centimeter, but also between 1 millimeter and 10 centimeter. But in this case, over very small fragments, we consider fragment densities instead of single objects treatment. So the network model, inside the network model, as we have seen before, we developed some analytics to better understand the interaction between the objects and the effects on the long term. So today we are mainly interested about spatial connectivity and local connectivity. So the spatial connectivity can be understood as the capability of a collision event to spread inside the network or inside the entire network, so through all the altitude shells. While the local connectivity is a capability of an event, collision event again, to spread in a certain region. So once a collision happened, let's say at 500 kilometers, what we want to do is to check the connectivity or the local connectivity. So around this point, how the collision spreads around the collision event. And so we use this second analytics to study these effects. So here are some main results of this pipeline. So what we consider is the case of three LEO reflectors at different altitudes, so 500, 800, and 1000 kilometers. They can perform station keeping for 7 years and then they decay at maximum drag. As we can see here, so the model has already been validated for both LEO and NGO, and the object population comes from SatCat and Isatiscos. So here the evolutionary results for the four object species in time on the left. So along 50 years of propagation, and on the right the cumulative collision distribution along the 50 years for the different use cases. So we can see that the model is capable to understand the evolution of all the species in time, and there's clearly a different effect depending on the altitude and the presence of the reflectors at different altitude shells, so in both the evolutionary plots and in the cumulative collision. Here the results for the spatial connectivity, so we see again that the presence of the reflectors at different altitudes make the spatial connectivity to increase in the first part and then to go closer to the baseline, so without the reflector, because mainly the collision effect reduces the average size of the fragments in time. And this is very interesting, and it gives a, a global idea of the phenomenon. But the local connectivity, here reported just for one of the three cases, is maybe more interesting because it gives the idea of the effects in that specific region. So in this case, the 800-kilometer region. So where the local connectivity is very high at the beginning, then it goes back closer but still higher to the baseline case, always because of the fragmentation effect. So in this case, we can see the reflector as a kind of cleaning effect for the debris um, derived from the collision. So to conclude, the present pipeline is an adequate modeling to better estimate the solar power satellite collision risk and allows to assess in more details the consequences of impacts with these very peculiar structures, and can in the future assist the operators in the orbit selection for solar power satellites mission. So there's of course some future works. So further analysis with the breakup model, which is very brand new model, um, better analyze connectivity, but also maybe to develop a special local connectivity that can follow up in time the reflector during the decay part, which can actually have different effect depending from the altitude shells. And again, analyze the impact of small fragments on the connectivity. And last but not least, include highly eccentric orbit and cislunar orbits into the analysis. Thank you so much for your attention. It's been a pleasure to attend ISE and Solar Power Satellites competition. And please feel free to contact me if you have any questions about this work and this presentation. Thank you.